All right, we're going to do a quick example of something related to those bi-connected components we talked about last time. If we finish quickly, then we could talk about something else. But for now, let's see how this goes. So I'm going to tell you about something called Cactus Graphs, and hopefully you've never heard of it. All right, so here it goes. All right, so let's start with some special graphs. Oops, fix this. Can you see this now?
We see your current slide and the next one.
Okay. Now? All good?
Yeah.
Hi, Clement. Okay, so let's start with a few quiz questions for you guys. You probably saw the answer for this when I was messing with the slide. So what's a graph? What does it look like when every vertex has degree 0? Now, what's degree? Degree is the number of edges that's incident on a vertex. So here we're saying every vertex has degree 0. So what does the graph look like?
Just vertices or nodes.
Just vertices and no edges, right? That's what it is. All right, so now let's make this a little bit harder. What's a graph look like if every vertex has degree 1?
It will look like a path.
Anyone else?
Or like a stick.
If you have a path, then the inside vertices have degree 2.
Oh, you're right.
It's like a bunch of vertices paired together.
That's right. So we're going to call this collection of disjoint edges. Okay. Because you can't have 2 edges touching each other. The moment you do that, you're going to create a vertex of degree 2. Clear?
Yeah.
Okay. Now let's make this even harder. What's the graph look like when every vertex is degree 2?
Okay, that one's a cycle.
Now it's a cycle. Is that right? Does everyone agree with this? Clement, you agree with this? So that turns out to be not quite precise. Why is it not precise?
Oh, because there could be multiple cycles.
How could there be multiple cycles?
2 separate cycles.
That's right. So it's possible that there are 2 disjoint cycles, in which case every vertex still has degree 2, right? So if you have a collection of, I should have said, disjoint cycles, then every vertex will have degree 2. Now, let me ask the last question. What if the graph is also connected and every vertex has degree 2?
One big
Now
cycle.
it's one cycle. Yeah.
Now it's just one cycle, right? So it's going to be a one single cycle, but it's also a simple cycle. What's a simple cycle? A simple cycle is one that doesn't touch itself except at the end. So you can't make a figure 8, for instance.
By touch yourself itself, you mean it doesn't touch a vertex again?
Right. Actually, A simple cycle is something that starts somewhere and comes back to itself, but along the way, it doesn't visit any vertex more than once.
Okay, thank you.
So that's a simple cycle. All right, so now that we've played around with some simple concepts, let me ask the next question. We're going to talk about something called a cactus graph. And this cactus graph is inspired by that picture of a cactus that you see there. And here's the definition. The definition says a connected undirected graph is called a cactus if each vertex of this graph belongs to at most one simple cycle. Actually, that doesn't. Something is wrong with the definition. I think it should say every edge belongs to at most one simple cycle, not a vertex. So I'm sorry, I did mess up on the definition. I need to go and verify this, but does everyone understand the definition? So this says that every edge is only part of one simple cycle. Now, part of at most one simple cycle. So here's an example of a cactus graph. Just to kind of set up the stage, we're now going to try and design an algorithm to recognize these cactus graphs, which means if I'm given a graph, an undirected graph, I want to know if the graph is a cactus graph. And here's an example of a cactus graph. Right. So over here, so my old definition is incorrect because this vertex, for instance, is part of two simple cycles. There's one here and there's one here. So it must be an edge. So an edge, every edge is part of at most one simple cycle. Does that make sense?
Yeah.
Yeah.
Clement, you're being silent. Everything okay? David and Adriana are also here. Good. Okay. So so that's our definition, and here's an example of a cactus graph. Now, how do we go about this? So what I'm going to tell you is that in order to recognize this, of course, we know what the input and output is. And the basic idea is going to be to start with bi-connected components. And I'm going to need you to help me to figure out how I go about doing this. Any thoughts on this?
So I think we will have to look at articulation points.
We'll have to look at articulation points, but that can be there even in non-cactus graphs as well. Okay, so how can I make you see this example here? How could I make this a non-cactus graph? What do I have to do for that? Can you suggest some ways of changing this to a non-cactus graph? Well, I could disconnect it. That way it would be a non-cactus graph. But let's say I want to keep it connected. How could I change this to a non-cactus graph?
We would have to insert an edge that connects to.
Connects what to what? give me an example of something that some change that would make it a non-cactus graph.
Would that connect two simple cycles?
That's good. That would work now, because now this edge here is part of this simple cycle as well as that simple cycle. Yeah, that's one. Any other possibilities? You want to remove that, Lazaro?
Yeah, yeah.
Like if you make it directed, right? Like that's like another way to make it
Yeah.
a cactus.
Okay, let's say yeah, good. So let's say we keep it undirected. How can I make this into a non-cactus graph? Let's try something simple. Let's say that, let me get my mouse back.
Wait, can I ask a question before we carry on?
Sure. Yeah.
What if we give it a bridge, would that be connecting to?
Well, there is a bridge here.
Oh yeah, yeah. Okay, never mind.
Oops, something happened. Give me a second. So this here, is this a cactus graph?
Yes.
It is. A simple cycle is a cactus graph, right? Everyone okay with this? How about this guy here? Let me see. My mouse keeps disappearing again. There you go. What about now? Is this still a cactus graph?
No.
Why not?
Because there's two simple cycles now.
Well, there were more than one simple cycles even in the graph on the right hand side. So that's not enough to say.
The two simple cycles, they share a edge.
Right. Okay. So simple cycles can share vertices, but they cannot share edges. That's the condition that we understood from this example, right?
So I have an idea. Like what if each bi-connected component only has the same number of edges as nodes or vertices?
Same number of edges as vertices, except for the degenerate case. Yeah, I think you'd be right, except for the case when the bi-connected component is simply an edge.
Oh, mm-hmm.
Right. So let me erase this here, clear it off. So it turns out one definition is that all bi-connected components are either just an edge or they're simple cycles and nothing else. Does this make sense?
Yes.
This is in line with what Ricky also said. The number of edges equals the number of vertices, except for the single edge case. So if I were to run bi-connected components algorithm on this graph on the right-hand side, what would I get? I would get I would get all these edges would be simple bi-connected components, right? And then this entire cycle would be one bi-connected component. This one would be another. This one would be another. This one would be another. This one would be another, and one here and one here. So each of those cycles would become one bi-connected component. So then your job turns out to be to essentially run the bi-connected component problem algorithm that I showed you last time, and then simply verify that each bi-connected component forms only a simple cycle with no more edges, or it's just a single edge. Does this sound okay to you? Everyone agree with this, understand this, and clear about it?
Yeah, that makes sense.
So for each bi-connected component, see how many simple cycles it has, and it should be one.
Well, it should just be a simple cycle and nothing else. One way to do this is firstly to check that every vertex has degree 2 and that the number of edges equals the number of vertices. That was our original definition. If you recall, this is what I asked you before. If you have a connected graph where every vertex has degree 2, what does it look like? It's a simple cycle. So here we're saying we run the bi-connected components algorithm, and every time, for every bi-connected component that we get, verify that it's just a simple cycle. Yeah, so if you're wondering how one can verify that something is just a simple cycle, as I said, you can verify two things, well, three things. It's connected, each vertex has degree 2, and the number of, well, in fact, that's enough, that it's connected and each vertex has degree 2. So even though the definition looks quite strange, quite difficult, it turns out that with bi-connected components, this is actually fairly straightforward problem. So one thing that's important is that the bi-connected components algorithm runs in linear time. It runs in the same time complexity as just depth first search. Because if you recall the way we wrote the code, we just run depth first search and collect some extra information along the way. Nothing new, nothing extra, nothing spectacularly extra happens there. Are you comfortable with this, or was this a bit too much?
How do we handle these cases where a vertex is part of a simple cycle, but has more than a degree 2 degrees?
Well, if let's see. So you do have examples of that over here. For instance, this vertex, I don't know if you see my mouse, but yeah, this vertex here has degree 4, right?
Mm-hmm.
However, when you run the bi-connected components algorithm, what will happen is that the two single edges would fall off, would become separate bi-connected components, right?
Yeah.
Then the triangle will fall out as one bi-connected component. And there, within that triangle, the vertex only has degree 2.
Okay, okay.
So, so for sure, what will happen when you run the bi-connected components algorithm is that all the edges that are sticking out, they will fall off first. They will get reported as bi-connected components. And then it will report the simple cycles that are hanging at the bottom. And then you will start to process them, and then it'll proceed. So it doesn't matter where you start, that's what it'll look like. Okay. So it's worthwhile for you to try this out, in order to convince yourself, it's worthwhile to run the bi-connected components algorithm that I gave you last time. I know I didn't share the slides with you, but Lazaro, if you remind me, I'll send those to you. Or did I send it to you last time? I can't remember.
No.
Okay, yeah, just remind me, I'll send that to all of you. And it's in pseudocode. You really, I strongly recommend that you go and code it up and convince yourself it works and it works correctly. Okay. I don't hear a resounding yes. You guys really need to implement these so that you can collect. Over time, you need to collect, make a collection of things that you have implemented that you're comfortable with, that you can reuse at whatever competition comes up next. Okay. All right. So that ends my slides for the Cactus graph, and I am going to go back to more graph algorithms. Are there any questions?
Not here.
Okay. Okay.
What happened?
So, sorry?
Oh, no, I was just asking what happened.
We finished the discussion of Cactus graphs, and I'm going to move on to a different set of slides on graph algorithms. Okay, here we go. All right, we are going to quickly talk about minimum spanning trees. I think this stuff you guys already know, so I'm going to talk about it somewhat quickly. Oh, wow. This set of slides here does not have the minimum spanning tree stuff. So give me a couple minutes, let me find this for you. Well, I know somebody asked me about strongly connected graphs. Let me prepare something better for you for next time. I'll talk about that. But today I want to talk about minimum spanning trees, and I don't see my slides. So give me a couple of minutes. All right. Oh, yes. Please hold on. Somebody's phone is ringing here.
I'm so sorry.
Sorry about that. All right, so here's the minimum spanning tree stuff. So is there anybody here who does not know what a minimum spanning tree is? Speak up now or forever hold your peace.
Minimum spanning tree is like the least amount of like length, not length, yeah, lengthwise to get from point A to point B, right?
No.
I okay.
All right, let's go over the definition. We are, first of all, we're assuming that we have a graph. Secondly, we're assuming it's an undirected graph, which means we're not concerned about direction. Third, we're assuming that we have what's called as a weighted graph, which means that every edge has a weight associated with it. And finally, we're assuming that it's a connected graph that we can get from anywhere to anywhere. So we're given a simple, connected, unweighted, undirected graph. First of all, a tree is any subgraph of this graph that doesn't have a cycle. You already know this definition. Tree is something without a cycle. A spanning tree is a tree that touches every vertex in the graph. So it spans every vertex in the graph, which means that a spanning tree is a tree that involves all the vertices, that connects every vertex to every other vertex, but the tree, because it's a tree, there are no cycles. So far, so good. Next, a minimum spanning tree. Well, before I tell you what a minimum spanning tree is, I have to tell you what the weight of a spanning tree is. The weight of a spanning tree is simply the sum of the weights of all the edges in that spanning tree. And a minimum spanning tree is the spanning tree of minimum total weight, which means the sum of the weights of all the edges is as small as possible. Now, in this example here, this is a undirected, weighted, simple graph. And the edges that are colored, that are shaded dark, are part of a tree. If you look at all the dark edges, you see that there are no cycles. And it's a spanning tree because it connects everything to everything else. So you could get from any vertex to any other vertex through the edges of the spanning tree. You don't need these other edges in order to get from place A to place B, no matter where to where. And well, you just have to take my word that this spanning tree is of minimum weight, that there is no other spanning tree that has a smaller total edge weight. Okay. So these minimum spanning trees are particularly useful because if you are a phone company and you're trying to lay cables that connect all the cities in the United States, then clearly what you may want to do in order to get everything connected to everything else would be, first of all, it should be a spanning tree. You don't want to create cycles because that's just using extra cable when it's not necessary. because a tree already allows you to get from anywhere to anywhere. And especially if it's a spanning tree, you can get from anywhere to anywhere within the United States. And if you make it a minimum spanning tree, then the total cable that you would lay would be as small as possible. It would be as minimum as possible. And that's why these things are valuable. So minimum spanning trees are optimal networks in some sense. So the next question we're going to ask is, how does one compute a minimum spanning tree? Well, first of all, how does one compute a spanning tree? Can somebody help me with that? Forget about minimum spanning tree. How can I compute any spanning tree in a graph? Let's say I give you this graph. How would you go about connecting a spanning tree?
Depth first search.
So if you just do depth first search, you get what's called as a depth first search tree. And the depth first search tree is a spanning tree, because if the graph is connected, the depth first search tree will visit every vertex in the graph. And so what you'll get, first of all, is a tree. And secondly, it would be a spanning tree. So you could also do breadth first search, and a breadth first search tree is also an example of a spanning tree. So those are all examples of spanning trees, but a depth first search tree does not have to be a minimum spanning tree. A breadth first search tree does not have to be a minimum spanning tree. It turns out that it's a little bit harder to find a minimum spanning tree. By the way, just to get your juices flowing, can you give me an example of a graph where the depth first search tree is not a minimum spanning tree? Any thoughts on this?
Like any weighted graph?
Any weighted graph. Well,
You might not always get the minimum spanning tree.
Yeah, but I want you to suggest a graph where depth first search will not find you. Well, I guess you can't guarantee that it won't find you. Right. Well, so perhaps that's not a very clever question to ask. But let me give you an example of something where depth first search may not find you the best. Oops, sorry. So let's say that your graph, oops, didn't work out. Why is it not letting me annotate? Right, this one should work. Nope, didn't work. Oh, what's going on? Okay, I am not able to annotate this for whatever reason, so I won't try this now. Let's move forward. So even if you take a simple cycle, okay. So let's say you imagine just 4 edges forming something that looks like a square, and let's say the edges are of weight 1, 2, 3, 4. Now, if I did depth first search from some vertex, there are two ways I could start out depth first search. I could either go to the left or to the right. Now, if the depending on which way I go for the depth first search, in the end, the depth first search will simply be one path. Now, depending on where I start, the edge that it will miss out needs to be the largest edge, and that may not happen unless you start at the right place. I don't know if that made sense to you, but in such cases, your depth first search is now going to give you a minimum spanning tree. It's going to give you some old spanning tree. Now, the next question we want to ask is, how can we be sure of getting a minimum spanning tree? And here, it turns out that a simple greedy algorithm actually gives you a minimum spanning tree. And there are actually many ways you could design this greedy algorithm. But today I'm going to show you a couple of different ways of doing this. The first one is called Cactus algorithm. You've probably seen this in your classes before. If this is your graph, you take all the edges, sort them in increasing order of weight, and then look at them, consider them one by one in that order of increasing weights. And if you can add it to the spanning tree without forming a cycle, go ahead and add it. So the first edge that you will add turns out to be 1, because 1 is the smallest edge here. The next one is 2. And again, by adding this, you don't form a cycle, so you add that in. The third one that it adds is another 2. And again, you can add this without forming a cycle, so that gets added. The next is this 4, and that gets added, no cycle yet. The next one is this 4. Again, when you add it, no cycle is formed, and so therefore you add it. Then comes this 6. If you were to add this edge, it would form a cycle with all these big fat edges, and therefore you discard it and throw it away. The following one you'll add is a 7. The next 7 you would consider would get deleted because it would form a cycle over here. And then you would consider the next one you would consider would be 8, which gets added. Then you consider this 8, and it turns out it forms a cycle over here, and so it gets discarded. Then you add this 9. Then 10 is considered, and it forms a cycle, and so that gets discarded. Then the 11 is considered, which also forms a cycle, and it gets discarded. Then the 14 is considered, and it gets discarded because it forms a cycle. So in the end, this is what you end up with. This is what you get, and that's your minimum spanning tree. And it turns out that you can prove theoretically that this is for sure a minimum spanning tree, that you cannot find. You may find other spanning trees with the same weight, but you cannot find a spanning tree with smaller weight than this guy here. And the total weight of this spanning tree is 4 plus 8, 12, 13, 15, 19, 21, 28, 37. So you have a minimum spanning tree of weight 37 in this graph. And no matter what you do, you're not going to be able to find anything better than that in this graph. So the algorithm is very simple to understand. It's called Cactus Algorithm, and you start with an empty graph. You start with no edges whatsoever, and then then you sort the edges according to increasing weight, as shown in step 4. Then for every edge that you consider, you check whether by adding it you form a cycle or not. If you don't form a cycle, you add it in. If you form a cycle, you discard it. And it turns out that this simple algorithm is very difficult to implement efficiently. And so you have to come up with some really smart data structures in order to make that happen. And so the best implementation turns out to be using something called a set implementation. And if you use the set implementation, this whole algorithm becomes reasonably efficient. and so you could then turn this into something that's useful and valuable. Any questions about this?
No.
So it's worthwhile for you to understand this algorithm because it's quite an elegant algorithm and also an elegant data structure and also an elegant implementation. By the way, over here we use an implementation of something called a set. Does anyone know how sets are implemented in programming languages?
For that set, I will use like a disjoint set union, the one that makes it of one.
That's right. So disjoint set union is one way of implementing sets. It turns out that in older programming languages, they used another implementation that used bit vectors, which was another nice way, clean way of implementing sets. However, the bit implementation is not a general implementation. It doesn't necessarily work easily for large graphs, whereas the disjoint union data set data structure is a very, very efficient implementation for sets. Maybe one of these lectures I'll explain what disjoint set union data structure is. For now, we don't need to bother with it. It's best for you to go and find the best implementation of Kruskal's algorithm and simply use this for now. That would be my suggestion. It turns out even using disjoint set union algorithm, there are nice tricks that one can use there and make it way more efficient than what you would get with a simple disjoint set union data structure. But again, we'll talk about this some other day. Are there any questions before I move on to a different algorithm for minimum spanning tree? Okay. The next algorithm is also a greedy algorithm, but it's called Prim's algorithm. And again, I'm going to show you with an example. And here's an example. In Prim's algorithm, in the earlier Prim's algorithm, the way we in Kruskal's algorithm, the way we implemented the algorithm was we sorted the edges by increasing edge weight, and then we considered them in that increasing order of weight, and then checked whether adding that edge was a good idea or not. If it formed a cycle, we threw it away. If it didn't form a cycle, we kept it. That was Kruskal's algorithm. Now Prim's algorithm, instead of dealing with edges in this sorted order of increasing weight, it starts from a single vertex and grows the tree as you go along until the tree becomes a spanning tree and touches every vertex in the graph. So that's what we're going to do. So we start with a single vertex, so there are no edges to start with. Then we look at all the edges going out of this vertex and pick the one that's of smallest weight. In this case, there's a 4 and an 8, so we add 4. Now our tree has 2 vertices, and we look at all the edges going from whatever we have grown so far and pick the smallest. In this case, we have an edge of weight 8, another of 11, another of 8. Either of these edges of weight 8 could have been added. We arbitrarily pick one. In this case, this version picks that edge over there. And now we continue. Remember, now we have a tree with 2 edges and 3 vertices. And we look at all the edges going out of this piece. And the smallest edge going out is a 2. So that's what gets added next. And then we continue with this process. The next edge that gets added is a 4. And then the next edge that gets added is a 2. And the next edge that gets added is a 1. And the next edge that gets added is a 7. And finally, the edge 9 gets added. And that ends the algorithm, because now you have touched every vertex in the graph. So one important thing to know is that any tree with n vertices has n minus 1 edges. Therefore, a spanning tree of a graph with n vertices is going to always have n-1 edges if it's a connected graph. And that's what you get. The moment you have added n-1 edges, the algorithm will stop. In the next slide, I'm going to show you the algorithm for Prim's in order to implement Prim's algorithm. But before doing that, let me stop and ask if anybody has questions.
Yeah, quick question. So throughout every step, we're taking the minimum of any visited node or just the previous node?
Well, we are looking at the blob, which is the tree that you've already constructed. You look at all the edges going out of this tree, and you pick the smallest edge going out.
Oh, okay.
Okay.
Thank you.
So occasionally you'll find this weird thing where it happened in this particular example, no, not here. So here you added 1. At this point, the edges that touch this graph, the smallest edge turns out to be 6, but 6 connects 2 vertices that are already part of the tree. So you ignore that edge and you throw it away. I don't know if that made sense to you. So it has to be an edge that goes outside, that connects something in the tree with something outside the tree. And among those edges, you pick the smallest one. So the implementation is quite nice. It uses something called a priority queue. I've shown here both the Kruskal's algorithm and Prim's algorithm next to each other so that you get to see how different they are, even though both are greedy algorithms. In Kruskal's algorithm, you sort the edges by increasing weight, and then you quickly look at those edges in that order and add the edge if it doesn't form a cycle. In Prim's, you always start with a single vertex. In this case, it starts with vertex R, which we call as the root vertex or the start vertex. And then it uses a priority queue. This priority queue consists of the weights of all the edges that lead out of the tree. So currently, when you're starting off, there's only one vertex, and any edge leading out of this vertex would be leading out of the tree, and all those edges would go on to the priority queue. So it processes these edges, puts them into the priority queue, and then pulls out the edges in the order of increasing weight. Because it's a priority queue, every time you delete something, you always get the edge that has the smallest weight. And when you get that edge, you check whether it's a valid thing to add. And if it is valid, you simply add it. And that's what you do here. So for each edge, you check if there's a simple condition that you check, and then based on that, you add it to the tree. The thing that you're going to check is whether what is it that you're checking? You check whether the other end of this edge is already in the priority queue. If it's already in the priority queue, then you already visited it. Then adding this edge would not be a good idea because it would form a cycle with the edges that you already added. And so then you would simply discard it. Otherwise, it gets added to the tree. And that's exactly what we did in the example that I showed you on the previous slide. And so this again does its job. Prim's algorithm is slightly easier to implement, and also in some sense is a little more efficient than Kruskal's algorithm. But if you use disjoint set algorithm, the Kruskal's algorithm is very, very competitive. So you could use either algorithm. Again, there are thousands of examples of the code that's available there on the internet, and you should just find one that you like and you are comfortable with and you understand, and use that for your own purpose. It turns out that it's not at all easy to prove that these algorithms do their job and actually find the minimum spanning tree. You need to understand a bit of the theory in order to convince yourself that they are correct. And I do have a slide here that shows why these minimum spanning tree algorithms are correct. I probably don't want to get into that right now. I don't think it's beneficial for you. But if you have questions, I am more than happy to explain either the proof or the algorithm in great detail if you wish. So I'm going to stop here and ask what questions you might have and what parts of this may not have been perfectly clear for you.
Is the Prim's algorithm, I mean, isn't there a version of the Prims where it checks if there are negative edges that form a cycle? A negative cycle.
A negative, so first of all, if there are negative edges, both these algorithms would work perfectly fine. There is no need to check for negative cycles. That's something in shortest path algorithm, not here.
Oh, okay.
Dijkstra's algorithm for shortest path has to worry about negative cycles. Kruskal's, the minimum spanning tree algorithm couldn't care less. In fact, in minimum spanning tree algorithm, if you take all the edges and add 10,000 to them, it won't matter, it'll give you the same answer.
Okay, no, I was thinking about the wrong thing, sorry.
You were thinking about Dijkstra's algorithm, and that question is very valid, yeah.
I think I know, I think I was thinking about Bellman-Ford.
Well, Bellman-Ford is necessary if you have negative cycles. Dijkstra's algorithm doesn't work for negative cycles.
Yeah.
So it's in the shortest path algorithm that you have to worry about negative cycles. Here, nobody cares. They can be positive, negative, whatever you want.
All right, thanks.
Okay. Other questions?
Professor, for maximum of spanning tree, we just turn all the edges negative and then do a minimum spanning tree.
I need to think about this answer. For now, I'm going to say what you're saying sounds right, but I'm not convinced. So I could flip all the weights and make them negative, and
then find the minimum spanning tree, and that means
then find the minimum spanning tree.
Spanning tree for the edges that aren't negative.
Yeah, I think it does seem to work, but I have to think about it. It sounds like something where we could run into a flaw. So
okay.
You need to be careful here.
Okay,
this is tricky. Yeah. I remember to have read this, but I'm not 100% sure of the answer. I would need a few minutes to think about it. Other questions? All right, so now minimum spanning tree is a very, very fundamental algorithm. You need it all over the place. But what you'll see next, which is Dijkstra's algorithm, is even more important because it's a practical algorithm that helps you to find shortest paths between vertices. Minimum spanning tree, I need you to remember, has nothing to do with shortest paths. Even though the tree as a whole has minimum weight, individual paths may be very expensive, may not be the shortest path. So shortest paths are not guaranteed by minimum spanning tree algorithms. In fact, it's possible that the shortest path might go all around and come back. If you have a simple cycle, a minimum spanning tree will have all the edges except one, which means that in order to even go from a vertex to its neighbor, you may have to go all the way around the cycle. Okay, so make sure you're clear about this difference between minimum spanning tree questions and shortest path questions. Path questions, you're going to need Dijkstra's algorithm, which is the next thing we will look at. Anything to do with the smallest network, shortest network, connecting things, you're going to need minimum spanning trees. That's either Kruskal's algorithm or Prim's algorithm. It's important to understand also or remember that Prim's algorithm uses a priority queue to implement. And that's very, very basic. It's one of the first classic examples of a priority queue. Kruskal's algorithm, on the other hand, does not use a priority queue. It simply sorts the edges, although you could sort using priority queue, but really it's a simple sorting followed by a disjoint set union algorithm that implements it. So they are implemented very differently. They're implemented using very different data structures. If you don't know what a priority queue is, you should go and read this. It's quite an important data structure. But if you have questions about it, I'm more than happy to answer questions about priority queues. How many of you don't know what a priority queue is? How many of you have never implemented a priority queue?
I think I implemented mostly once.
Okay, so that's something I would, again, strongly recommend that you go do it. There are many implementations of priority queues. Priority queue is a concept. It's an abstract data structure, but there are many wonderful implementations of priority queues. And it turns out that different implementations are better for different algorithms. For Prim's algorithm, it turns out that there is this fancy priority queue implementation called Fibonacci heaps that turns out to be the most efficient implementation of priority queue for making Prim's algorithm very efficient. Again, you don't need to understand Fibonacci heaps, but if you're going to pick a implementation that works fast, then that's something that I would consider finding. I would consider finding a priority queue implementation that uses Fibonacci heaps and using it here. Fibonacci heaps are described in several of your textbooks. You're welcome to go read it. If you want me to explain this, again, I'm more than happy to do it, but it's probably not worth your time at this point. Any other questions? Anything else I could answer? Any theoretical questions?
And just in overall, like actual solving problems, I've never actually seen a minimum spanning tree problem. Only like actually solving for the minimum spanning tree.
Yeah. All right. I will definitely look for one. This Saturday, I have a cactus problem question for you, but I'll try and locate a minimum spanning tree problem. Sure.
Okay.
I will do. I'll try my best. But you're right. They're not very frequent. The more frequent questions have to do with shortest paths. Those are very popular. It's a lot easier to design competition questions about paths and instead of spanning trees. But yeah, I'll see if I can find one. So since the Saturday competition will have a question on cactus graphs, it also means that you're going to need to brush up your bi-connected components. Okay?
Oh God.
You know, If you want to go and locate one, you're welcome to do that. But maybe you don't need to implement bi-connected components. Who knows? Any questions for me? I think I'm going to stop here for the day and leave shortest path and Dijkstra's algorithm for next time. It's an important topic, and I want to do that more slowly, and perhaps even also discuss a little bit of priority queues when I do that. Again, priority queues are used for Dijkstra's algorithm. Very, very important. So we need to go over that very carefully. Also, it's a good example of something called dynamic programming, which is really our next topic. So I'm going to finish Dijkstra's algorithm. Then I'm going to do all pair shortest path, but all pair shortest path has some subtle points that are quite difficult to understand. So I want to spend some time on it. And once you have mastered those two, you would have already seen good examples of dynamic programming. And after that, we'll be ready for dynamic programming, which is one of the most challenging topics in this general domain. Other than things like network flow, dynamic programming can be super challenging. So we're going to do that in the next 3-4 weeks. How does that sound?
Yeah, sounds good.
Yeah, sounds good.
Okay.
Good.
All right. Perfect. Okay, let's stop here, guys.
All right. Thank you, Professor.
All right, Lazaro.
Professor.
Have a good day, Professor.
Thank
Good night, Professor.
you.